In this video, we're going to discuss the galvanic cell notation. So galvanic cells can often be very cumbersome to draw, and so we'd like a more compact way of writing a galvanic cell when we need to. This shorthand way of writing a galvanic cell is called the galvanic cell notation. It's also sometimes called a shorthand notation or a cell diagram. So here's a galvanic cell composed of a zinc anode and a copper cathode. And again, anytime we talk about this galvanic cell, we wouldn't want to have to draw this whole thing out and label all the parts. Again, that could be very cumbersome. So there's a shorthand way, a more compact way that we can express a galvanic cell such as this. So from that galvanic cell, if we looked at it, we could see that the zinc portion was the anode, and the copper half reaction, or copper half cell, was the cathode. So here's our overall reaction. So how could we express that galvanic cell more compactly? Well, it would look something like this. So look at this and let's label the parts. So for this galvanic cell notation, we would put the anode half cell on the left. The anode half cell is always on the left in the shorthand notation. And you can see here, we have the zinc solid, that's the reactant, separated by a line. And then we have the product second, the aqueous zinc, which you can see over here. Then we have a double line, we'll talk about that in a second. And then we have the cathode half cell on the second half, or the right hand side of our notation. We have the reactant first, and again the reactant for the anode would be copper 2 plus aqueous. Then we have a line separating the two, and then we have the product copper solid. So we always write the anode half cell on the left, the cathode half cell on the right. Now the double line in between the two represents the salt bridge. So we'll always have a salt bridge in our galvanic cell, and that's represented by the double line there. The single lines are what we call a phase boundary. If you notice zinc here, the reactant is a solid and the product is aqueous. So these two things are in different phases. So anytime you have a reactant and product in different phases, you put a single line, what we call a phase boundary. If they're in the same phase, both were aqueous or both solid, we would put a comma. On here, again, we have the phase boundary separating the reactant, aqueous, and the product, solid. So study that and be sure you understand those parts. So galvanic cells are often constructed under standard conditions, where we have 1 molar for all solutes, 1 atmospheric pressure for gases, and at 25 Celsius is our temperature. Under standard conditions, the concentrations or pressures may be left out of our cell notation. So for example here, we assume everything to be 1 molar concentrations for the aqueous solutions because we're not given any information. However, we often can put the concentrations such as 1 molar here and 1 molar here for our aqueous solution. So sometimes they're left off, sometimes you'll see them, but you will always need to put the concentrations if they're non-standard. So if we had some concentrations that were anything other than 1 molar, so we had non-standard conditions, we do want to show the concentrations or the pressures if these were gases. Again, for solids, the concentrations are constant, so we don't need to put those. So let's see if we can write the shorthand notation for the galvanic cell for this following reaction. Pause the video and give it a try. Okay, so here's the galvanic cell. You don't have to draw this, but again, this would be fairly bulky to draw. Also from our reaction, we should be able to identify that the magnesium is losing electrons. So the magnesium half reaction, that's my anode half reaction, and the cathode reaction would be the hydrogen here. So again, let's write our equation. Here we have the magnesium, the anode half cell on the left. We have our cathode half cell on the right. Now notice here, the hydrogen is aqueous and hydrogen on the product side is a gas. So we must have some electrode in order to conduct the electrons into our solution. So review the galvanic cell video and appreciate that here we have to use a platinum electrode in this reaction. So for our cathode, since we need the platinum, we would put our hydrogen aqueous, that's our reactant first. Hydrogen gas is our product, so that goes second. And then we would put the platinum at the end. If we had platinum over here on the anode side, it would go at the beginning. Here in the cathode side, it would go at the end. So we have our salt bridge in between the two and our phase boundaries. And again, we also have a phase boundary here separating the gas from the solid. So even though platinum is not in our overall equation, we do have to appreciate that since we don't have a solid like we do with magnesium, we have to add an electrode there. Okay. Now we could also write this under standard conditions. We could add the concentrations. For aqueous, it would be 1 molar. And for hydrogen gas, it would be 1 atmosphere. We don't have to put those since this is assumed to be standard conditions, but under non-standard conditions, we would have to put the concentrations that were given. So let's try one more. See if you can write the galvanic cell, the shorthand notation for this reaction. Pause the video and give it a try. Okay. So let's break it down into our half reactions. We have the anode half reaction and the cathode half reaction. And also I noticed, like the previous reaction, the cathode reaction does not have any solid metal that I can use as an electrode. So I'm going to have to use platinum to conduct the electrons down into this solution. So our shorthand galvanic cell notation would look like this. We have our anode half reaction, the reactant first, phase boundary, and then the product, because these are in different phases, my salt bridge, and then we have the cathode half cell. Here I have the reactant first, and we don't have to put the coefficients, the 2, we don't have to put those in our overall equation. So we have our EU3 plus aqueous, and then EU2 plus is my product. Notice that these are in the same phase, so we don't put a phase boundary, we just put a comma. So pay attention to that. But as I said before, we do have to have a platinum electrode, or you could have used graphite, but platinum's a good choice. And we have a phase boundary separating those. So we have our salt bridge, and then we have our phase boundary between these guys, but no phase boundary here. But we do have to have a phase boundary between the platinum and the aqueous. So be sure you understand the parts for this galvanic cell shorthand notation. Be sure to understand when to use a phase boundary, when not to, and be sure that you appreciate when to include, say, a platinum electrode in your in your galvanic cell notation. Again, if we needed one over here, we would put the platinum first over here. Of course, we don't need one, but we would put it over here, platinum solid. Okay, so study these and be sure you can write the shorthand notation.